We'll start in 1 minute. Today we'll be in Chapter 8, Section 2, Simplifying Radical Expressions. In Section 8.1, we assumed that a variable represented a real number so that, for example, the square root of x squared equals the absolute value of x. In Section 8.2 and beyond, we will assume that a variable represents a positive real number so that we can write the square root of x squared equals x without the absolute value symbols. The next thing is the product property of radicals. So product in arithmetic and algebra implies that we're going to multiply. If we let n be a positive integer, and if the nth root of a and the nth root of b are real numbers, then the nth root of a times b is equal to the nth root of a times the nth root of b. So that works the way that we probably wish that it would. This property will come in handy. The product property of radicals will be applied to simplify radicals with more complex radicands than were encountered in Section 8.1. In 8.1, we simplified square roots of perfect squares. We simplified cube roots of perfect cubes, and so on. But the radicand won't always be a perfect power. So here's the procedure for simplifying a radical with index 2, the square root. The first thing we do is identify the largest perfect square factor of the radicand. Then we write the original square root as a product of two square roots, where the radicand of one of those two square roots is the largest perfect square factor found in step 1, and the radicand of the other square root is the radicand of the original square root divided by the largest perfect square factor. We simplify the square root of the perfect square and then multiply it by the other square root. Okay, so we'll demonstrate that procedure with some examples. So the first one, the square root of 20. 20 is not a perfect square, but it has a whole number factor that is a perfect square. 4 times 5 is 20, and 4 is a perfect square. So what we do is we rewrite the square root of 20 as the square root of 4 times 5. So 4 is the largest perfect square factor of 20. And then use the product property of radicals. The square root of 4 times 5 is the square root of 4 times the square root of 5. And then we simplify the square root of 4 to 2. The square root of 4 is 2, so our simplified answer is 2 times the square root of 5. Okay, so that demonstrates in one example what you're going to do whenever you simplify radicals. Okay, the next one is the square root of 63. 63 is not a perfect square. What's the largest whole number factor of 63 that is a perfect square?
9.
Yeah, 9. 9 times 7 is 63. 9 is a perfect square. So rewrite the square root of 63 as the square root of 9 times 7. Then apply the product property of radicals. The square root of 9 times 7 is equal to the square root of 9 times the square root of 7. And the square root of 9 is 3. So our simplified result is 3 times the square root of 7. Okay, we'll do a few more examples involving square roots. They'll get a little more challenging, but not much. So the first one on the upper left, simplify the square root of 75. Uh, 75 is not a perfect square. The largest factor of 75 that is a perfect square is 25. 25 times 3 is 75. So the square root of 75 is the same as the square root of 25 times 3. Then the square root of 25 times 3 is the square root of 25 times the square root of 3. Then we simplify the square root of 25, which is 5. And so our simplified result is 5 times the square root of 3. Okay, the next numerical example, the square root of 98. 98 is not a perfect factor. What's the largest whole number factor of 98 that is a perfect square? So you can type that in online if you want. The largest factor, the largest whole number factor of 98, that is a perfect square. 13?
14.
14? No. 14 is not a perfect square. Okay, how about 49? 49 times 2 is 98. 49 is a perfect square because 7 to the second is 49. So brushing up on your arithmetic can be very helpful. So we rewrite the square root of 98 as the square root of 49 times 2. And then applying the product property of radicals, this is the square root of 49 times the square root of 2. The square root of 49 is 7, so our simplified answer is 7 times the square root of 2. All right, now we'll do some square roots of expressions with variables. Simplify the square root of x to the 15th. The exponent on 15, or sorry, the exponent on the variable x is 15, which is not even. So this is not considered a perfect square. The largest factor of x to the 15th that is a perfect square is x to the 14th. X to the 14th times x is x to the 15th. So rewrite this as the square root of x to the 14th times x, which is x to the first. So you might want to remember, or if you have to, review the properties of exponents that we covered a few weeks ago. If you have a to the m times a to the n, you add the exponents, a to the m plus n. So in this particular case, x to the 14th times x, well, x has an exponent of 1, so this is x to the 14 plus 1, or x to the 15th. X to the 14th is a perfect square because the exponent 14 is even. So we apply the product property of radicals, and we can write this as the square root of x to the 14th times the square root of x. And then the square root of x to the 14th is x to the 14 divided by 2. The index is 2. 14 divided by 2 is 7. So our simplified result is x to the 7th times the square root of x. Okay, the next one, simplify the square root of y to the 7th. The largest factor of y to the 7th that is a perfect square is y to the 6th. So rewrite the square root of y to the 7th as the square root of y to the 6th times y to the 1st. Y to the 1st is just y. Then the square root of y to the 6th times y is the square root of y to the 6th times the square root of y. And then simplify the square root of y to the 6th. The square root of y to the 6th is y to the 3rd. So our simplified result is y to the 3rd times the square root of y. Okay, the next two examples, we have numerical factors and algebraic factors. So simplify the square root of 18 times x to the 27th. Okay, we combine what we did earlier. We do it separately. First let's focus on the numerical factor 18. What is the largest perfect square factor of 18? 9. 9 times 2 is 18, and 9 is a perfect square. The largest perfect square factor of x to the 27th is x to the 26th. So we can rewrite this as 9 times 2 times x to the 26th times x inside the square root. We can rearrange the factors first, if that helps. So let's do that. Let's write this as a single square root with the perfect square factors farther to the left. So we have the square root of 9x to the 26th times 2x. Then using the product property of radicals, we can write this as the square root of 9 times x to the 26th times the square root of 2x. And we can simplify the square root of 9 times x to the 26th. The square root of 9 is 3. The square root of x to the 26th is x to the 13th. And we multiply that by the square root of 2x. Okay, so this is our simplified result. Okay, the next one, simplify the square root of 72y to the 41st. Okay, the largest factor of 72 that is a perfect square is 36. 36 times 2 is 72. The largest factor of y to the 41st that's a perfect square is y to the 40th. Y to the 40th times y is y to the 41st. Okay, so rewrite this as the square root of 36 times 2 times y to the 40th times y. Then we'll rearrange the factors so that the perfect square factors are farther to the left. The square root of 36 times y to the 40th times 2 times y. Then simplify the square roots of the perfect square factors. The square root of 36 is 6. And what's the square root of y to the 40th? Does anybody know what's the square root of y to the 40th? 20? You mean y to the 20th? Yeah, y to the 20th. I know what you meant, but so 6 times y to the 20th, and then multiply that by the square root of 2y. Hey, these aren't too bad. If you practice them enough, they get easy with practice. Okay, now we're going to do the same sort of thing, but with radicals of higher index. So remember the index of a square root is 2. The next level is cube roots, so the index will be 3 on these. So it's this similar procedure when simplifying a radical with index 3. First, identify the largest perfect cube factor of the radicand. And then write the original cube root as a product of 2 cube roots, where the radicand of one of those 2 cube roots is the largest perfect cube factor found in step 1, and the radicand of the other cube root is the radicand of the original cube root divided by the largest perfect cube factor. Simplify the cube root of the perfect cube and multiply it by the other cube root. Okay, so here are some examples where we simplify cube roots. Okay, simplify the cubed root of 40. Or we can also say the third root of 40. So we want to find the largest factor of 40 that is a perfect third power or a perfect cube. So let's see, what are the perfect cubes? 1 to the third equals 1. 2 to the third equals 8. 3 to the third is 27. 4 to the third is 64. So 2 to the third equals 8. 8 is a perfect cube, and 8 is a factor of 40. So we rewrite this as the cube root of 8 times 5. Then apply the product property of radicals. The cubed root of 8 times 5 is equal to the cube root of 8 times the cube root of 5. And the cube root of 8 is 2. So our final answer is 2 times the cube root of 5. When you're doing these problems in Newton, you have to make sure that you type in the index. Perhaps everyone will forget at times to type in the index. If you don't type in the index, it interprets it as a square root. So remember the index. Okay, the next one, simplify the cube root of negative 54. Oh, let's see, the cube roots are, or the perfect cubes, I mean, are 1 to the third equals 1, 2 to the third equals 8, 3 to the third is equal to 27, 4 to the third is 64. So 27 times negative 2 is negative 54. But for a cubed root, when the radicand is negative, we can write this as the product of negative 27 times positive 2. And then the cube root of negative 27 times 2, that's equal to the cube root of negative 27 times the cube root of 2. The cube root of negative 27 is negative 3. So our final answer is negative 3 times the cube root of 2. Remember, the cube root of a negative real number is a negative real number. Okay, the next one, simplify the cube root of negative 250. We want to identify a factor of negative 250 that is a perfect cube. Okay, the perfect cubes. 1 to the third is 1, 2 to the third is 8, 3 to the third is 27, 4 to the third is 64, 5 to the third is 125, 6 to the third is 216, 7 to the third is 343. So I've already mentioned the one that we need. Yeah, negative 125 is a perfect cube of negative, it's a perfect cube factor of negative 250 because the number negative 5 to the third power equals negative 125. So we'll rewrite this as the cube root of negative 125 times 2. Then use the product property of radicals to write this as the cube root of negative 125 times the cube root of positive 2. And the cube root of negative 125 is negative 5. So our final answer is, or our simplified result is negative 5 times the cube root of 2. Okay, the next one, simplify the cube root of 128. Okay, the perfect cubes, we're looking for a positive perfect cube this time. The perfect cubes are 1, 8, 27, 64, 125, 216, 343. See it? What is it? Yeah, 64. 64 is a perfect cube. It's also a perfect square, but we're looking for perfect cubes here. 64 times 2 is 128. So this is the cube root of 64 times 2. And that's the cube root of 64 times the cube root of 2. And the cube root of 64 is 4. So 4 times the cube root of 2 is our final result. Okay, we'll switch to some variable expressions inside cube roots. The cube root of x to the 10th, simplify that. Well, with variables that have exponents, how do we know that it's a perfect third power? If the exponent is a multiple of 3, if you have a variable raised to an exponent that is a multiple of 3, then it's considered a perfect cube or a perfect third power. 10 is not a multiple of 3, but 9 is, and x to the 10th is x to the 9th times x. So we can say the largest factor of x to the 10th that is a perfect third power is x to the 9th. So we rewrite this as the third root or the cube root of x to the 9th times x, because x to the 9th times x is x to the 10th. Then apply the product property of radicals. This is the cubed root of x to the 9th times the cube root of x. Hey, how do we simplify the cube root of x to the 9th? X to the 9th is a perfect third power because 9 is a multiple of the index 3. Okay, so we can simplify that. We remove the radical, write the variable x, and what's the exponent? It can be found if you divide 9 by the index 3. 9 divided by 3 is 3. And then we multiply x to the third times the cube root of x. So this is as far as we can simplify that expression. Okay, the next one, simplify the cube root of y to the 26th. The exponent 26 is not a multiple of 3. So y to the 26th is not a perfect cube. We want to find the largest factor of y to the 26th that is a perfect cube. If an exponent is a multiple of 3, then that variable with the exponent that's a multiple of 3 is considered a perfect cube. Okay, well, if the exponent that we start out with is not a multiple of 3, then we work backwards. Is 25 a multiple of 3? No. Okay, the next integer less than 25 is 24. Is 24 a multiple of 3? Yes. So y to the 26th is equal to y to the 24th times y to the 2nd. So we rewrite the cube root of y to the 26th as the cube root of y to the 24th times y to the 2nd. We know that y to the 24th times y to the 2nd is y to the 26th. But we want this because y to the 24th is a perfect cube. It's okay to simplify this directly, the way that we have it, or we can write it as a product of cube roots, the cube root of y to the 24th times the cube root of y to the 2nd. So how do we simplify the cube root of y to the 24th? We remove the radical, write down the variable y, and how do we determine the exponent? Yeah, 24 divided by the index 3. 24 divided by 3 is 8, so we get y to the 8th times the cube root of y to the 2nd. Okay, now we'll do a mixture where we have cubed roots of constants times variable parts. Hey, the cube root of 81x to the 19th. The largest factor of 81 that is a perfect cube is 27. 27 times 3 is 81. 27 is a perfect cube. The largest factor of x to the 19th that is a perfect cube is x to the 18th. So we rewrite this as the cube root of 27 times x to the 18th times 3 times x. And you can verify that you're doing it correctly by multiplying. Okay, then the cube root of 27 times x to the 18th times the cube root of 3x. We simplify the cube root of 27 times x to the 18th. The cube root of 27 is 3. The cube root of x to the 18th is x to the 18 divided by the index 3 is 6. So 3x to the 6th times the cube root of 3x. Okay, the next one, simplify the cube root of negative 24 times y to the 41st. Okay, so a perfect cube factor of negative 24, well, there are two of them, but we want the one that's negative. So negative 8 times positive 3 is negative 24. So we're going to, in the process, we'll eventually simplify the cubed root of negative 8. And what's the largest factor of y to the 41st that's a perfect cube? Okay, the exponent 41 is not a multiple of 3, so remember we work backwards from 41. The next integer lower than 41 is 40. Is 40 a multiple of 3? No. So we keep going. The next integer less than 40 is 39. 39 is a multiple of 3. So we're going to rewrite this as the cube root of negative 8 times y to the 39th times 3 times y to the 2nd. So on the next one, I'll go into more detail than is necessary, but it might help. I'll write this as the cubed root of negative 8 times the cube root of y to the 39th times the cubed root of 3y to the 2nd. Hey, we can simplify the cube root of negative 8. That's negative 2. So in other words, negative 8 is a perfect cube because the number negative 2 to the 3rd is negative 8. The cube root of y to the 39th is y to the 39 divided by 3, or y to the 13th, multiplied by the cube root of 3y to the 2nd. So this is our simplified answer. Okay, we'll look at some higher index radicals. We did a bunch of square roots, and we did a bunch of cube roots. Let's try our luck on a 5th root and a 4th root. We're just going to apply the same idea. Simplify the fifth root of n to the 32nd. So with variables and exponents on those variables, how do we know that we have a perfect fifth power? If the exponent is a multiple of 5, then it's considered a perfect fifth power. 32 is not a multiple of 5, so we work backwards to 31. Is 31 a multiple of 5? No, so then we keep going. The next integer less than 31 is 30, and 30 is a multiple of 5. So our intermediate step, we rewrite the fifth root of n to the 32nd as the fifth root of n to the 30th times n to the second. Because n to the 30th times n to the second is n to the 32nd. We add the exponents. Okay, then write this as the fifth root of n to the 30th times the fifth root of n to the second. And we can simplify the fifth root of n to the 30th because n to the 30th is a perfect fifth power. So when we simplify the fifth root of n to the 30th, what is the exponent on n going to be? Yeah, it's going to be 6. Divide 30 by 5. 30 divided by 5 is 6. So we have n to the 6th times the fifth root of n to the second. Okay, the next one, simplify the fourth root of 32 times m to the 20th. So find the largest factor of 32 that is a power of 4. So what are the powers of 4? 1 to the 4th is 1. 2 to the 4th is 16. 3 to the 4th is 81. So we've already gone past the one that we need. 2 to the 4th equals 16. 16 is a factor of 32. And 16 is a perfect fourth power. So we'll keep that in mind. What about the largest factor of m to the 20th that is a perfect fourth power? M to the 20th is a perfect fourth power because the exponent 20 is a multiple of 4. So we'll rewrite this as the fourth root of 16 times m to the 20th times 2. And then the fourth root of 16 m to the 20th times the fourth root of 2. The fourth root of 16 is 2 because 2 to the 4th is 16. And then the fourth root of m to the 20th is m to the 20 divided by 4, or m to the 5th. We multiply that by the fourth root of 2. So this is our simplified answer. Okay, the next level is radicals with fractions or quotients. We have a quotient property of radicals. So we let n be a positive integer if the nth root of a and the nth root of b are real numbers and b does not equal 0, then the nth root of a over b is equal to the nth root of a over the nth root of b. Okay, so let's simplify the radicals of quotients. So here we have the second root, that's the square root. So the square root of 50m to the 7th divided by 49n to the 14th. So we can rewrite that as the square root of 50m to the 7th in the numerator divided by the square root of 49n to the 14th in the denominator. So we want to simplify both of those square roots. So in the numerator, the largest factor of 50 that's a perfect square is 25. 25 times 2 is 50. The largest factor of m to the 7th that's a perfect square is m to the 6th. In the denominator, 49 is a perfect square, and so is n to the 14th. So we can, in the process of simplifying the numerator, we can simplify the denominator completely in the next step. So in the numerator, we rewrite this as the square root of 25m to the 6th multiplied by the square root of 2m. And in the denominator, we can simplify this all at once. The square root of 49 is 7. The square root of n to the 14th is n to the 7th. And then our final answer, the square root of 25 is 5. The square root of m to the 6th is m to the 3rd. So the numerator is 5 times m to the 3rd times the square root of 2m divided by 7n to the 7th. That is as far as we can simplify. Okay, the next one, simplify the square root of 300x to the 6th divided by 169y to the 8th. So let's write it as a quotient of square roots. So the square root of the numerator, square root of 300x to the 6th, divided by the square root of 169y to the 8th. So we want to simplify both the numerator and denominator. Start with the numerator. What's the largest factor of 300 that is a perfect square? Uh, 100 times 3 is 300. The largest factor of x to the 6th that is a perfect square. X to the 6th is a perfect square because the exponent is even. And then the denominator, the largest factor of 169 that's a perfect square. One 169 is already a perfect square. Y to the 8th is already a perfect square. So the numerator, we'll rewrite that as the square root of 100x to the 6th times the square root of 3. We can simplify the denominator because we're just taking the square root of a perfect square. Square root of 169 is 13. The square root of y to the 8th is y to the 4th. And now we're just one step away. The square root of 100 is 10. So it's more conventional to put the numerical factors farther to the left. So I'll write 10 times the square root of 3 And then the square root of x to the sixth is x to the third. And the denominator is 13 times y to the fourth. Okay, we're down to about a couple of minutes. Let's try the first cube root of a quotient. Simplify the cubed root of 375 over 27. So we can write this as the cube root of 375 divided by the cube root of 27. The largest factor of 375 that is a perfect cube is how much? 125. Yeah, 125 times 3 is 375. So we can rewrite the numerator as the cubed root of 125 times the cubed root of 3. The denominator, the cubed root of 27. 27 is a perfect cube, so we simplify that to 3. And then the last step, the cubed root of 125 is 5. So the numerator is 5 times the cubed root of 3, and the denominator is 3. This is our simplified answer. Okay, so we're down to, well, we're out of time now, so that's a good place to stop, I guess. We'll continue on in Chapter 8 on Monday.